Mechanically operated switches are switches that are not operated by a human being, they're operated by a machine. Limit switches are a common example of this. So there can be all kinds of things that activate the switch. Position typically operates a limit switch, whereas pressure, temperature, these are other types of switches that are sensitive to other things in a machine. So limit switches are usually operated by contact or something pushing on them. There are several different standards for symbols. There's the NEMA and the IEC standards. The NEMA standard, you can see the switch symbol for a normally open limit switch and a normally closed limit switch, and you can recognize the difference pretty readily with IEC symbols. They're similar, but there are slight differences in the standards. One's not better than the other, it just depends on where you're at as to which one you'll typically see. But you can interpret either one pretty straightforwardly. It's not difficult to understand. So these switches are switches that have to be very reliable. If you look at the picture I've got here, it looks like a very over-engineered switch, and this is not the kind of switch you're going to find when you open your microwave and that senses the door. Typically the way that microwaves operate is they have limit switches that are very cheap and small, but they have multiples of them, and that's how they get high reliability. This type of switch is very reliable because it's just very well designed, and it's designed to take millions and millions of cycles. Temperature switches or thermostats just say detect temperature changes. Now typically this type of switch does not detect a particular, how can I say this? It doesn't give you a temperature reading, in other words. So it doesn't say, okay, it's 10 degrees, now it's 20 degrees, now it's 30. They're usually set to trigger at a particular level. So the switch will turn on at a certain temperature or turn off at a certain temperature. And a lot of times one of the slight wrinkles about these is that they typically have a lot of hysteresis, or at least a certain amount of hysteresis. Some of it is intentional. What that really means is that, let's say the temperature is going up, okay, so the temperature is at, let's just make it up, 70 degrees, and let's pretend that the switch triggers at 75 degrees, okay. So temperature is at 70, it goes to 71, 72, 73, finally it hits 75 and the switch comes on, let's say, okay. So the switch is on, it's conducting electricity, and let's say the temperature goes all the way up to 80, and then it starts to drop, and the temperature drops from 80 to 89, or 89, that's not a drop, 79, 78, all the way down to 75. What will often happen is the switch will not turn off at that point. The temperature actually has to drop below. Maybe it'll have to go to 74 or 73 degrees before the switch will change states back to off. So that's a pretty common thing, and it's sort of a feature, if you will, of temperature switches. It's something to expect when you have a temperature switch like this. The NEMA symbols and IEC symbols are shown there, and they're slightly different. The NEMA symbols are the ones I'm used to, and it looks like my one graphic is slightly covering the other. I'll fix that before you get to the presentation files, but you can see them. They're a little bit different, but that symbol, either one of those, represents a temperature type of switch, something that changes based on temperature. Pressure switches are pretty common. You may not know it, but you often have several pressure switches involved in any refrigerant system you have. For example, air conditioners, heat pumps, even air conditioning in your car often has a high pressure switch and a low pressure switch. And what those switches do is they prevent the system from operating if the pressure is too high or too low. Now you might wish that it would operate anyway, but the purpose of these switches is just to make sure that the machine does not destroy itself, right? That it doesn't damage itself, because in refrigeration systems, often the oil, and in fact everyone that I know of, the oil is mixed in with the refrigerant, so the refrigerant has to flow around, and if you don't get oil to the compressor is going to burn out. So you really want these switches to be operational in the refrigerant system, so that the system only operates when the pressure range is appropriate. But you can get pressure switches for gases, for liquids, for all sorts of things, and they're sensitive to pressure. Some are made to work with gases, some are made to work with liquids, and they're not made to work with the opposite. In fact, they can be damaged with the opposite. So there's a wide range of these switches. I'm showing you large classes of switches really in this presentation. The standard symbol for NEMA you can see there in blue, and for IEC you can see there in sort of a yellow color. And again, these typically have some hysteresis, just like the temperature switches have. The reason you wouldn't want a switch that has no hysteresis is because if you're just right at the level where it's supposed to turn on, the temperature or the pressure may vary a little bit about that, and the switch may turn on and off very rapidly and either damage the switch or give data to the control system that doesn't make sense because the pressure is above and then below and above and below over and over, and that's not good. That's not something you typically want in controlling a system. So there's the standard symbols. You might notice that all of these switches have either normally open or normally closed contacts. Sometimes they have both. It just depends on the design of the switch, and you can often select within a family of pressure switches whether you want it to come with normally open or normally closed contacts. Level switches are a little bit different. They're used to sense level in a tank, for example, and this is a float type of switch, and basically the switch is designed so that when it's hanging it's in one orientation, but when it floats it sort of flips over, and there's a gravity based switch that opens up or closes as the level switch senses level. So you just hang these at various levels within the tank, and then you can tell where the level in the tank is within at least two pressure switches. So these don't have infinite resolution. They are stepwise, right? If one switch is on and another switch is off, well then you know the levels between those two switches for sure. But other than that, you couldn't say where in the tank the level actually is located. It's somewhere between those two switches. Now there are other types of level switches. Obviously pressure switches could be used to detect level. A lot of times there are pressure sensors that are not on-off type sensors. They measure the pressure, say, at the bottom of the tank, and because of fluid statics you can calculate the actual level in that tank. So you don't get an on-off reading then, you get a continuous reading, but that's a different type of sensor. Right now we're talking about switches that are either on or off, and notice that all of these fall into that type of category where they're either a true or false is what's given from them. Now there are many other types of switches besides these, but these are the most common and the ones I want you to be familiar with, at least for now.